Hi, it's Theo, and this is the Rollercoaster FRQ. Okay, so we have this roller coaster of mass m. It starts at a height h, and it kind of falls down, and it goes around this loop-de-loop with radius r, and it's also frictionless. And yeah, we'll get to a in a second, but main thing, mass is m, starts at height h, this has radius r. Okay, so we're gonna look at the top of this circle, and the problem is telling us that the normal force due to the track at this point is 0. So I'm just going to draw a free body diagram at that point real quick. So if normal force due to the track is 0, the only force acting on this is going to be gravity. We can also say that because this force is pointing completely towards the center of the circle, and so it's the only force and it's pointing completely towards the center of the circle, we can say that acceleration is equal to v squared over r. So sum of forces equals mass times acceleration. So there we go. Now we just cancel out the m's. Okay, so that is our velocity at the top of the roller coaster. Okay, so now we're being asked, based on this, what is the required starting height such that at the top of the roller coaster there's no normal force due to the track? Okay, so for this I'm going to set up an energy equation. So at the beginning, our energy is just mgh because it's at rest. At this point, we've got some kinetic energy. That's going to look like a 1/2 mv squared sort of thing. And then some sort of gravitational potential energy. Now the height that we're at the top is actually going to be equal to 2 times the radius. Okay. And then as you can see up here, v squared equals gr. So I'm going to substitute that in. And that equals, boom. Now we just cancel out mg, and we can say that h is 5/2 r. In other words, given a certain radius of that circle, you can find how high you want to be to start based on 5/2. So kind of a little bit above the top of the circle. It's actually not kind of what you might think is that it would be exactly the top of the circle, but we don't want our velocity here to be 0. So we gotta start a little bit above 5/2. Okay, so next we're asked to draw a free body diagram at point A, given this data. So at point A, my mass is not quite straight. It's kind of like going along, maybe like this. Okay, there's always gravity. And in this case, there's also some normal force from the track kind of pointing towards the center of the circle. So I'm going to kind of point it that way. And then notice that this angle is theta, because it's kind of perpendicular to the track, pointing towards the center. So that is our free body diagram. And then finally, we are asked to find the speed at this point. So looking at this problem, there's a couple of reasons why I'm going to use energy equations here. A, because force equations are better for acceleration, not for velocity. And also because we kind of already have energy equations set up, so it's going to be easy for us to kind of plug stuff back in. So we can compare it to the energy at the start of the ride, which is mgh, but we now know that h is equal to 5/2 r. So that's our initial energy. And then at this point, we have some kinetic energy, but we also have some gravitational potential energy. So let's just think about what that would be. So if this is our height reference to 0, the hypotenuse is r, So this is going to be r sine theta because it is kind of the opposite component of this triangle. So you have r sine theta, and then, so we don't want r sine theta though. We want this part, like the kind of the leftover. So we can say this is r, right? This whole thing is r, minus the r sine theta will get us this height. So that will give us the height. Okay, so now we'll just solve for velocity. So moving things over to the left, and I'll also take out an mg. And I'll combine like terms, so we've got 5 halves r minus r, that's 3 halves r, plus an r sine theta. Wait, actually, I'll take out an mgr. mgr, and we've got 3 halves plus sine theta. Okay, we can take out mass, and then I'll also multiply both sides by 2. So we've got so that is our speed at point A. And kind of one way we can check that is that this should work for all theta, right? So let's just take some of our limits. So if theta is equal to 0, 2 sine theta is 0. So that comes out to 3gr. Which sort of makes sense because, I mean, I'm not going to go ahead and solve this all again, but it's going to be definitely greater than the speed at the very top, but less than the speed at the bottom. And the speed at the bottom should be, well, the speed squared at the bottom should be 5gr. That's because 1/2 v squared will end up being 5 halves. So at the bottom, our v squared should be 5gr, and at the bottom, our theta is going to be 90, or pi over 2. So sine pi over 2 is 1. This becomes 3 times 2, and there that's 5gr. So v squared will be equal to 5gr. So that all seems to make sense. Okay, great. So that is the whole problem. Let's just go over each step to summarize. So given that there's no normal force due to the track at the beginning, the speed will be square root of gr. In addition, the starting height will have to be 5 halves r. And this is a free body diagram of a given point A with an angle theta to the horizontal axis. And then finally, here is the speed at a point A given a certain theta, r, and then whatever planet you're on that will determine the gravitational constant. So yeah, thanks for watching.